Okay, so we're going to continue on. The next topic is polynomial regression. So we've got this data here. So let's say we had a bunch of midterm grades, and the objective was to be able to predict what the final exam grade would be of a student, given that they had a midterm that already took place. So, for example, so if we had a couple of we have a few training examples where if the midterm was 89, the final exam mark that the student got was 96. Similarly, if the midterm was 72, the final exam they got was 74, and so on and so forth. So we're trying to find a prediction model where, given a midterm exam mark, what would the predicted final exam mark would be. So this is obviously a nonlinear relationship. So what we're going to do is we're going to try to fit a quadratic model to this data. So we're going to introduce the one feature, which is just the midterm exam by itself. And then we're going to introduce another feature, which is just taking the midterm exam and squaring it so that you're able to fit a nonlinear polynomial model to this data. So the first question asks you to add a new feature x squared and to fill in that table. Well, it's pretty easy. All you have to do is just take each of these features and square them. And then what you have to do after is to feature normalize the table. So you're going to have to take the mean and the standard deviation for each of the features and then feature normalize. Don't do the final exam, obviously. That's the output value that you want. And then you're going to compute gradient descent for 3 iterations with a learning rate of 0.75. And then you can also certainly double check on MATLAB the code that you wrote for Lab 1. You can just use multivariate here, where you have multiple features, and you can double check to see whether or not you're getting it right. Okay, so I think I have a copy of this somewhere. Yeah. No, that's not it. Where is it? Ah, here we go. Fantastic. So here we go. This is polynomial regression. Okay. So the first task is to complete this table, and that's pretty easy. All you have to do is just take every feature and square it. So we have 7921 because that's 89 squared, 5184 that's 72 squared, 8836 because it's 94 squared, finally 4761 because it's 69 squared. Now all you have to do is just compute the mean and the standard deviations for each of these features. We can certainly do that. So the first mean is 89 plus 72 plus 94 plus 69 divided by 4, and we get 81. And then the standard deviation is 1 over 4 minus 1, and then you're adding up the deviations with every single training example for the particular feature, and then subtract it with the mean of that. So 72 minus 81 squared, 94 minus 81 squared, 69 minus 81 squared. So if you add this all up and you find what this is equal to 12.3558. Okay, so you can certainly do this with the second feature as well. I won't insult your intelligence. You can do this on your own. You got 6675.5, so 6,675. And finally, the standard deviation for this particular feature is 2009.0558. Come on. Okay, so now all you have to do now is feature normalize. So that's the next part. So let me put in that table again, which is over here. So these were the old features. Okay, so this was, if you recall, this is 7921, 5184, 8836, 4761. So all you have to do is just, so this is the first example, the second example. Again, I'm just going to do one, just to be sure we're on the right track, and then you can go ahead and do the rest yourself. So these are the new features. So the first one is equal to 89 minus 81 divided by it was 12.3558. Okay, And then this is the first feature. Second feature, so don't forget about the final exam. I mean, don't forget about my final exam, but just forget about the final exam of this particular problem. And the second feature is 7921 subtract 6675.5 and 2009. 558. Okay, and this is equal to 0.6475. It's equal to 0.6199. And I'll let you do the rest of this. So for the second one, we had minus 0.7204, minus 7.7424, and then we can do the rest of them ourselves. So this was 1.0521, 1.70754. Last training example is minus 0.9712, minus 0.9524. Okay. All right. So now what we have to do now is polynomial regression. So if you look, we had 0.75 and n is equal to 3. Initial parameters is 0. So let's see here. So our data matrix, okay. So we prepend column of 1s. We get 0.6475, 0.6199. So this is the first training example normalized. This is the second training example normalized. 424. Okay. 1.0521, 1.0754, minus 0.9712, and minus 0.9524. Okay, so these are just taking the training examples that I just normalized previously and just putting into a data matrix and making sure you prepend a column of 1s. Okay, also the expected marks, 96, 74, 87, and 78. Okay, so this is question number 4. And then we had so let me see here. We had our learning rate of 0.75. We had 3 iterations to compute. Also, we initialize all the parameters. Okay, there's only 3 features here, right? Because you have the bias term plus the midterm mark by itself and then the midterm mark squared. So there's only 3 features. So then what we need to do now is simply the update rule that we had from before. It's the linear algebra formulation. So alpha over m x transpose x theta minus y. So this is the update rule. We're doing polynomial regression. Okay, so let's just do the first iteration. This should be instinctual by now, but let's just go ahead and go through the motion. Okay, we update this with the previous iteration, which is certainly just all zeros. Subtract, and then we had 0.75. So this is, remember, this is all zeros. 0.75 over 4, and then x transpose was 1, 1, 1, 1, right? So I'm just taking this matrix x and just transposing it all, so all the rows become the columns. So this is 0.6475, 0.7284, 1.0521, and minus 0.9712. And let me just spread these out so that it looks a little even. And then 0.6199, minus 0.7424, 1.0724, and finally minus 0.9524. So this is x transpose. Let me move this around so we can get a better glimpse of what's going on. Okay, so, and then we multiply this by the matrix here. Okay, so bring this all the way down. We're multiplying by this matrix. Okay. Times 0, 0, 0 minus the expected vector, which is this guy. Okay, it's not copying the 74. I'll just put it in myself. Okay, so whenever you take a matrix and you multiply by the 0 vector, it just goes to 0, so that goes away. Alright, so now we're just left with just a minus of this vector, and remember that you're multiplying everything by that. So finally we get, so this is the first iteration. Okay, so this is minus 0.75 divided by 4. And then we take the X transpose matrix, which is this guy here. Okay, and then multiply this by the negation of Y. Oops. Okay, so when you compute all this, I won't bore you with the details, but you get this is equal to 62.8125, 4.5030, 4.4638. So that's after the first iteration. Okay, and you want to compute the cost. Remember, we should probably compute x theta minus y. It's a good idea to do this, so that you're using it for the next iteration. In this case, you take the X matrix, which is this guy here. Okay, I'll copy it, X's and all, and I'll remove what I don't need. This is 0.7284. Minus 0.7424. Okay, so you take this matrix, come on, you take this matrix, multiply this by the vector here, so 62.8125, 4.5030, and 4.4638, and subtract this with the vector here, so 96, 74, 87, 78. So when you compute this term, when you compute this, this becomes what are the details? So this is minus 27.5021, minus 17.7843, minus 14.6483, and minus 23.8184. Okay, so this is what that would be, and then if you want to compute the cost, it's just taking every single one of these values and summing them together and dividing by 2 times m, which is 8 in our case. So it's just minus 27.5021 squared plus minus 17.7843 squared. Right? Yep. And then plus minus 14.6453 squared plus minus 23.8184 squared. And then when you add this all up, we get 231.8055. And that's pretty bad. Very high cost at the first get-go. Okay, so iteration 2. I'll show you one more iteration. I'm just going to write down the final result in the end. These I don't want to take up too much of your time here. So this vector was here, this guy here, all these values. Okay, so this is the previous vector minus, and then you have to take x transpose, which I have over here. And also don't forget to multiply by alpha divided by m, which is 0.75 divided by 4. Okay, and then what you do now is you take, so this guy was theta, this guy is alpha over m, this guy is x transpose, and then all you have to do is just take x theta minus y and to put it right beside, that's what you have to multiply with here. So minus 27.5, 5021, minus 17.7843, minus 14.6483, minus 23.8184. And again, I'm not going to insult your intelligence by, by showing you how to compute this. You already know how. Finally, the result that you get in the end, okay, is going to be, let's see here, equals 78.5156, 3.9687, and 3.8823. Okay, and then j of theta. All right, this cost is simply equal to, let me see, did I compute it? Hold on. So the cost here was 25.948. Alright? This, if you want to go through yourself, it's just 1 over 2m and then x. Okay, you can do that yourself. And then finally, the last iteration, you can do that on your own. This is 82.4414, 4.0601, 3.9306. Right, and the cost associated with assigning these parameters to the data is 13.0983. Alright, and that's it. Okay, and those are our parameters for the polynomial regression. Okay, now let's get on to stochastic gradient descent. So basically, we're going to use the same data that we saw before, but let's just assume it's been randomly shuffled, because part of the gradient descent algorithm is to randomly shuffle your data. So what we're going to do is we're going to apply stochastic gradient descent using this data. And the difference between stochastic gradient descent and normal gradient descent is that you you perform an update using each training example individually. So you perform an update using the first training example, you update the parameters, then you use the second training example, you update the parameters, and so on and so forth, until you get to the end. Okay? I'd like to make a little hint that I will not ask any stochastic gradient descent questions, because they just take a very long time to compute, because you have to perform 4 updates for each example that you have. So in this case, we have 4 parameters because you're including the bias. So every example is going to give you 4 updates. So once we run through these examples, you're going to have 16 updates. And it's just going to take a while to compute by hand. So don't worry about this for the midterm. But I'm going to obviously cover this question for the sake of completeness. Okay, so let's just do stochastic gradient descent. Okay, so let me see, did I write down these features? Yes, I did. So we're going to use this data before. Okay, so let's just recap. Okay, so the hypothesis that we have, okay, is we currently are exploiting this. We're using 3 features plus a bias term. Okay, we also know the problem is given as 0.5. Okay, so if you take a look, they give us a learning rate of 0.5. All the initial parameters are 0. Compute 1 full iteration. So that means that you're going to use each training example once, and you're going to update the parameters. Okay, so so here we go. So compute 1 full iteration of SGD. I'm going to call this stochastic gradient descent as the acronym SGD, just to make things a little easier. So if you recall the algorithm, it's actually not bad. So what we're going to do is you repeat k times, where k is somewhere in the neighborhood of 1 to 10. This number is subject to experimentation, so you just simply have to play around with it until you get, good results. So repeat k times for the following steps. So for every training example from 1 to up to m, okay, what you're going to do is you're going to update after each training example. Okay, for j is equal to 0, 1, 2, all the way up to n. And usually the 0th feature is equal to 1. Right, so. Okay. Also, there is an individual cost that is associated with these parameters. So what's happening here is that when you compute the cost, what you're doing is you're figuring out how well this training example fits with the parameters. So this is not a universal cost, because with batch gradient descent, or the gradient descent where you're taking a look at all training examples, you're actually calculating what the average cost would be, or the cost overall, in order to use those parameters to be able to assign it to every single point in your data. With stochastic gradient descent, you only have the one example available, so when you compute the cost, it is only for that particular feature. So what people normally do is they compute the individual costs of each of the training examples, compute them, and then average them over, every 1,000 or every 100 or so you can have a good idea of, or have a sense of, how the cost is decreasing over time. And if it's decreasing over time, then you probably have a good setup. Okay, but anyway, so just the cost for the single training example is just the deviation between the expected and the true output for just that one example. Okay, so to make things easier, what we're going to do is we're going to do the sum definition. You can't really do this by linear algebra because you're only using one example, and it's a little tricky to do it because you're doing an update for every single example. If you're doing a simultaneous update for just one example. So, iteration 1. So what you're going to do is you're going to compute the bias term. You're using the first example. So, sorry, let me just cut this. So for iteration 1, so we're going to use the first example and compute the update. All right. Okay, and this is x, 0, 1. All right. Okay, so this was equal to 0 because those are our initial parameters, right? So alpha is 5, and then I need to mention that we initialize the parameters to be all 0. Okay? So this was 0.5. And our hypothesis was a sum of 3 features that are weighted by the parameters theta. And these are all zeros because we initialized them all to be zeros. So you're going to get 0 minus 0.5, and then the expected output was minus 0.5. Okay, so you're going to get minus 0.5. Okay, and this becomes 0.25. And then you're going to update the next parameter using the same rule. So if you notice this difference here between the first example, the hypothesis minus the first, this term here is constant throughout each of them. So all you really have to do is just substitute 0.5 into here, but then you have to change the feature so that it is the first feature now instead of the 0th feature. So if you pull open our data from before, this guy here, the first feature is actually 0.5. So this is 0.5. This was minus 0.5 from the previous step. And so we get minus 0.5, 0.5, 0.5, which is actually minus 0.125. Okay, because this is technically 1/8. So right, half, 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 so this is 125. Okay. Now we're going to do the next update for the second parameter. Okay, so this is 0.5, and this is also this is minus 0.5 from before, and then you need the second feature of the first training example. In that case, if you take a look, this is equal to 1, so this is just 1. So finally, this is just equal to minus, or this is positive 0.25. Or not minus, minus 0.5, minus 0.5. Oh, sorry, yeah, yes. Hold on a minute. Yeah, so this is just 0.25. Okay, finally, you have a third parameter, which is theta 3 minus alpha. First example again. This time you're using the third feature from the first example. So if you take a look here, this is equal to 2. This was minus 0.5 from before. This is 0.5. Okay. So this is just equal to 0.5. Okay. Now if you want to calculate the cost for assigning this feature to the current data, so our hypothesis, okay, is now, let's see here, it was 0.25, and then minus 0.125 x1, okay, and plus 0.25 x2, and then plus 0.5 x3. Okay, and all you have to do is just substitute this in. So minus, and then the you have y squared. In this case, we have 0.5. So this is y, and when you compute this, you get 1.1289. Oh, sorry, this is not 0.5. Sorry. Yeah. Okay, let's just do this again. So we have, so this is 0.25 minus 0.125 times x1, which is 0.5, plus, okay, let's just move this. Okay, and this is 0.25 times x2, which is 1, and then minus or plus 0.5 times 2, and then subtract with that, and you get this. Okay, that's good. All right. So, whoops, made a little mistake. Right. This is equal to, I am really sorry about that. This is equal to minus, and then minus 0.5. So this becomes minus 0.25, okay? And, okay, this is all 0.5s. Well, I sincerely apologize for that. So, 0.5, 0.5, right? And this is positive, so this becomes minus 0.25. And this again is positive, so you get minus 0.5. So the model is minus, minus, minus. This is minus and minus. Okay? So they're all negatives. I sincerely apologize, because the input example is minus 0.5, so when you subtract a negative, you should get a positive, and that's what we get. Okay, I sincerely apologize for that. So, so we have this. Okay, so now what we're going to do is we're going to do the second example. Okay, so we only did the first example. So now we're going to do the second example, first iteration. All right. So we know currently that we have the following parameters after this iteration. So not iteration, after this example. Okay. So now all you got to do is just do the computation. So theta 0 with theta 0 minus alpha, and then we have the second training example with the corresponding expected output and the first feature, the zeroth feature of the second example, and we can certainly assume this is 1. Okay, let me just put in the table that we had from before, and where is it? It's this one. Alright, so when we do this, alright, so this is equal to minus 0.25. This is 0.5. Okay. Now this is theta 0 plus theta 1, whatever. So this is minus 0.25 minus 0.125 x1. Oh yeah, we had it from before. So this is just, this guy is up here. Okay. So, and then this guy is 1, and then that's 1 as well. So we got theta 0 minus 0.25 minus 0.5, and then we're going to do minus 0.25 minus 0.125. The example here, so you have 1, 0.2, and 2, so 1, 0.2, and 2. Subtract this with the expected output, which is 1, and that's it. Okay, so in this case, we have minus 0.5, and then this is minus 2.425. And this guy here, this is going to be constant for the rest of the updates for this particular training example. So we're gonna, so we're gonna remember this, and then finally we get equals 0.9625. Okay. Now let's do the next update. Okay, well, we know that this guy here is just here, so that's 2.425, right? And the, let's see here, the first feature of the second example is just 1, all right? First feature of the second example is just 1. This is 1, 0.5. So when this guy here was minus 0.125. So this is minus 0.125, and this is minus 0.5, minus 2.425, and then multiply that by 1. This update we get is 1.0875. Okay, and then let's do the last bit. So okay. Oh, sorry. 2. And then I'm doing this for the second. Alright? So if you take a look at the table, the second feature for the second example was 0.2. So this is 0.2, right? This is minus 2.245. This is 0.5. And this was minus 0.25. So if you substitute everything, you get minus 0.0075. Okay? Finally, you have theta 3 minus second. This is a third second. Okay? Looking at the table, third feature, second example was 2. So this set this to 2. This is minus 2.425. Right? This is 0.5. This is minus 0.5. So if you substitute everything in, you get 1.925. Alright? And then finally, if you want to compute the cost, I won't bore you with the details. You can do that on your own if you wish. So when you do the cost, it's just h of theta okay, using the premise we had before, you get 23.9953. Okay, now I'm just going to write out the last couple of examples for you because you know how to do this already. So theta 0, theta 1, theta 2, and theta 3. This was minus 0.293, minus 0.168, minus 0.2586, 1.2983, or 2973, and the associated cost for this example alone was 0.1326. And finally, if you want the last example for the first iteration, this is equal to minus 0.4249, minus 0.0361, minus 0.1927, finally, minus 1.2709. And the associated cost is 0.0015. Also, the question asks you to find the average cost. So all you're doing is you're just adding up all the costs that you computed for all of the examples together. So the first one was 1.1289. Then we had 23.9953 plus 0.1326 and 0.0015. We divide this by 4. And we get 6.3146. Okay, this is taking really long, so I'm going to let you do 6 and 7 yourself. So if you take a look, 6, well, what they're doing now is you're just getting the parameters that you had from after the one full iteration, so these parameters here, so this set of parameters here, and you're going to run through stochastic gradient descent one more time. And then 7, the average cost, is it going up or down? Why do you think it's happening? You can pretty much answer that yourself. So I'm going to let you do 6 and 7 on your own because you have the tools in order to do that now. Okay? So that's it for practice problems 3. So let me see how much we have covered so far. Logistic regression regularization. Okay, so I'll be able to do logistic regression and regularization and this, and then we'll take a break, and then we'll do the rest of the stuff after. Okay. So we're going to do a logistic regression now. Alright. Just getting my notes ready. Okay, logistic regression. So let's take a look at the third problem set. Sorry, this is this here. Fantastic. Okay, so logistic regression. So it's pretty much almost exactly the same in terms of the update rule for gradient descent. The only thing that's changed is the hypothesis, and the hypothesis is simply the you have the sum of weighted values, but you're applying the sigmoid to the output. And the cost function is also changed. Instead of it being a sum of squared differences, it is the cost function is changed, and we'll talk about that later. So what we have now is we have two features. We have 4 examples where we have 2 examples belonging to the positive class where y is equal to 1. And we have 2 examples that belong to the negative class when y is equal to 0. So now what's going to happen is we have our initial set of parameters all set to equal to 0. And given that our learning rate is 0.1, we're going to compute n is equal to 3 iterations of logistic regression. And we're going to show what the parameters at each iteration looks like, as well as the cost function. And then finally, we're going to plot the decision boundary that is defined by the parameters. And we're going to make sure that the positive points are crosses and the negative points are circles. And we're going to see how well this decision boundary delineates between the two of them. Okay. So, logistic regression. So, let me see. I think I managed to take a snapshot of that table. Okay, good, fantastic. Okay, so we set alpha is equal to 0.1. Okay, and we are going to compute n is equal to 3 iterations. Right? And let's see here, the initial parameters are simply all 0. Okay? Okay, so recall algorithm. So in terms of gradient descent, it's exactly the same, but what is different is the hypothesis value. It's no longer just a sum of weighted, it's a sum of weights. You have to apply the sigmoid function to it as well. So recall algorithm, gradient descent is still the same, but update has changed. Okay, the update has changed. And specifically, so this cosmetically looks the same as you have seen in, linear regression. Okay. Sorry, let me rewrite this. This is a really important rule that I don't want to forget. Okay, but the hypothesis is the sigmoid function. Okay, this is the sigmoid function. Okay. Also, the cost function has changed. Right? Cost function has changed. So, it's equal to average cost. Come on, get out of here. and minus. So this was covered in class, so I encourage you to look at the notes for more details. But this was the new cost function for logistic regression. Okay, so you're summing over these negative log probabilities. Okay, so if you want to do this by linear algebra, which I highly encourage you to do so, well, let's do it. So linear algebra. Okay, the update rule looks like this. Okay, so what's happening is x times theta is a vector, and what you're going to do is you're going to compute the sigmoid value once you compute this vector. So x is our data matrix as before. See if I can copy it from somewhere else, because I'm really lazy. So yeah, here we go. Fantastic. This stuff is the same as before. All right. Very nice. Okay, let me just get rid of this. Okay. Fantastic. Okay, that's good. Okay. All right. So, 1. Okay. So this notation still stays the same as before. All right. So basically what's happening here is once you compute x times theta, use sigmoid function on each element. And use the result. Okay? Alright, so let's just go ahead and do this by linear algebra approach. It's going to be a little easier for us. Okay, so it's the first iteration. So okay, so this is all 0, right? These are all zeros. Okay, and then our learning rate was 0.1. Number of training examples was 4. And now we have to write the transpose of this matrix. So where was it? This guy here. Don't want to get confused. So yeah, we'll leave this here. So remember to prepend the column of ones. So we have 1, 1, 1, 1, 1, 2. Sorry, 1, 1 more 1. And we have 1, 1, 1, 1, 1, 2, minus 1, 0, 1, 0, 0, minus 1. Okay, so this is x transpose. This guy is alpha over m. This guy is theta. And then finally we just simply write out the matrix by itself. So we have G of one, 1, 1, 1, 2, 0, 1 minus 1, 0, 1, 0 minus 1. Multiply this by your vector of vector of initial parameters, so there's only 3 of them. And subtract this with the labels that you want. So this is 1, 1, 0, 0. Okay, so if you take this guy as x, this guy is theta, and this guy is y. So when you multiply this and this together, this gets eliminated. So what's happening here is you are... Sorry, let me just... Actually, I'm going to take this instead. Okay, it's not copying that, but whatever, that's fine. So so this is 1, 0, 0, minus 1. Okay, so what's happening is you apply the sigmoid to a vector of zeros. Okay? Now the sigmoid function at 0 is equal to 0.5, right? Because if you have g of z 1 over 1 plus e to the minus z, right? If you have g of 0, you have 1 over 1 plus e to the 0 is 1. So this is simply 1 over 2, which is 0.5. Oh, come on. Yeah, I'll just leave it like that, 0.5. Okay? So finally, okay, so this becomes all 0.5s. Okay, so when you subtract these together, okay, you subtract these together, so this generates. And when you do this matrix vector multiplication and compute all this, what you get is zero, 0.05, 0.25. Okay? And then the cost function is a little more difficult. I'm only going to show you how to compute this once, and then I'll leave it up to you to do the rest. So it was 1 over m Yeah, I'll leave the regularization last. I'll do that the next after. I'll take a break after this. Oops, where are we? Here. That's good. Okay, minus. Okay, that's good. And so this is the cost. So what's going to happen now is when you decide to do the sum, so you have 1 over 4, and then what's going to happen, let's just get the table of values so that we're consistent. Okay, so when y is equal, so let's see here, so we're going to do the first example. When y is equal to 1, this part of the sum, the first part of the sum activates. So you're going to have minus log, and then h of theta x of 1, right? Which is just simply, so h of theta, so what's going to happen is, this becomes, let's see, okay, so, let me just write this down. So h of theta, okay, is 1 over 1 plus e to the minus theta transpose x. And theta was, so theta transpose x is simply equal to, we have 0, and then this is 0.05 x1 plus 0.25 x2. Okay, there's no bias term because that was set to 0. So this is what the hypothesis is going to be. Because of the negative. So this is the new hypothesis, okay? So it's going to be substituted into every single one of these values. So you have log, and then you have h of theta x1. Actually, so you have log, and then 1 over 1 plus e to the minus 0.05, and then x1 is 1. Okay, and then minus 0.251, which is x2. Okay, subtract, and then when y is equal to 1, this sum activates, so log 1 over 1 plus e to the minus 0.05 times 2, that's x1, and then minus 0.25 times 0, okay, and then minus, and then this sum activates, the second part of the sum activates because y is equal to 0 now, so you get log 1 minus, so minus 1 plus 0.25 times 0, okay, finally minus log 1 minus. Zero and then minus 0.25 times 1. Okay, so when you compute all this stuff, j of theta is finally equal to 0.6931. Okay, that's how you compute it the first time. I'm not going to do it again, so I'll let you figure that out on your own, but I'll just give you the answers. Okay, so this is iteration 2. Okay, so make the update. So this was 0, 0.05, and 0. Oopsie, I made a little mistake. This is 0, unfortunately. I apologize. So I forgot an extra decimal point. So, okay, so this is okay, 0. Okay, this is going to be annoying. So 0, 0, 0, 0. Yeah, so there's an extra decimal point there. I sincerely apologize. Okay, so now we have 2, 5. Okay. Apologies. So 0.1 divided by 4, that's alpha over m. So this is theta. It's alpha over m. And then we multiply by x transpose, so 1, 1, 1, 1. 1, 2, minus 1, 0. 1, 0, 0, minus 1. Okay. And then finally, we have this bracket, so you have g. And then x transpose, so this is 1, 1, 1, 1, 2, 0. 1 minus 1. 0, 1, 0, minus 1, multiplied by the vector, which is 0, 0.05, 0.025. Subtract this with the expected value, 1, 1, 0, 0. Okay? So when we compute this vector here, we get 0.075, 0.1, minus 0.05, and minus 0.025. Okay, so when you compute this, and then when you finally take the sigmoid of this, okay, what's going to happen is that you get a new vector such that it becomes 0.5187, 0.5249, 0.4875, and 0.4937. Okay, so you're taking the sigmoid of every element of this multiplication and applying the result. So take sigmoid all values in x times theta. Okay, so this was x theta and this is y. Okay, so when we finally compute this stuff, all right, so we get theta 0, theta 1, theta 2. So this is 0, 0.05, 0.025, minus 0.1 divided by 4. This is, okay, I'm going to copy this guy. G transpose. Okay, so we get 1, 1, 1, 1, 1, 2, minus 1, 0, 1, 0, 0, minus 1. So when you take this guy and subtract by minus 1, you finally get minus 0.4812, minus 0.4750, 0.4875, we're subtracting 0 and 0.4937. Okay, just a little sideline there. So when you finally compute this, we get minus 0.0006, 0.098, finally 0.0494. Okay, so the cost function, I'm going to let you do that on your own. This is simply equal to 0.6625. And then the third iteration I'll also let you do on your own. It's no need to beat you over the hammer with computations. So parameters are minus 0.0018, 0.144, 0.0731, and the cost associated with this is equal to 0.6341. Okay, so the decision boundary that is generated by this, the decision boundary, is simply minus 0.0018 plus 0.144x1 plus 0.0731x2. Right? So what we can do is that you set this equal to 0. That's where the decision boundary is bounded. And then if you rearrange and solve for x2, you'll get x2 equals 0.025 minus 1.9687. So this is the decision boundary, and I've got a nice figure that illustrates where, where the points are as well as the decision boundary itself. It's actually quite nice. So it's actually this guy right here. Okay. Also, here's a picture of the points and the associated classes to make sure that we're on the right track. Okay. So all the positive classes, so these guys are over here, and these guys is the negative classes over here, and this is the decision boundary. So this is x2 equals 0.025 minus 1.9687x1. So any point on the decision boundary on the one side is classified as positive. Anything on the other side is classified as negative. Okay, so I'm going to take a break here and come back, we'll do regularization, then we'll finish off with the last part of the tutorial.